Swayam Prabha. Digital India. Educated India.
It gives me immense pleasure to introduce our speaker for today, Dr. Avhishek Chatterjee. He is an assistant professor in the Department of Electrical Engineering at IIT Madras. He was a postdoctoral research associate at the Coordinated Science Laboratory of the University of Illinois. He has a PhD in electrical and computer engineering from the University of Texas and a master's in telecommunication from the Indian Institute of Science, Bangalore. His research interests primarily include mathematical study of stochastic and information networks, amongst others. We are honored to have you here, sir. Thank you.
Thank you. Thank you.
Please give him a warm welcome.
Thanks for the introduction. Thank you, and hope you're enjoying the IIT Madras campus. So many of you here for the first time. Okay, so everybody has seen black box. Enough of them. Okay, good. Anybody go into the sports like our ground where you can run Vatsa Stadium? No. Okay. You should go there. That's a nice, you get very nice breeze in the evening. So after the session is over, maybe it's a good time. Okay, but you have to remove your shoes before entering some part because it's okay. So what I'm going to talk about. So I don't have any pretty pictures to show. As I said, my work is mostly mathematical or computational. But we can play some games, nice games, and I can give you some motivations about certain problems which connects to very beautiful math. So there are two aspects to my work. One part, as I said, stochastic and information networks. Okay. So what does it mean? So what is a network, first of all? Okay. Network means there are a lot of things, agents or entities that are interconnected. Like we call road networks, right? So the national highway network. What are they? Highways are going from one place to another and connecting different cities. So it's all of India. So suppose you have national highway networks. So this is essentially different nodes that are connecting to different parts of India. Right? So this is one network. It's very different from another network, which is electric grid. What is electric grid? Your power supply. This is nothing but your power supply network. That's also all over India. So mostly in India, states have their own networks, but there is an interstate connection also. Like sometimes if you have surplus power in a particular state, it can be given to the next state which does not have power. So these are all networks. Okay. But what is the most popular network these days? Internet. And on top of internet, I don't know if kids here are like too young to use, but social networks, anybody uses? I don't encourage, though I work on it, but I don't encourage kids to use it. It's not a good idea. Even adults like us get carried away very easily. So, because there are a lot of nonsense going on, so it's better to stay away. But we have to deal with it also, it's important. So, my generation, it used to be, I grew up in a generation where it was Orkut. You may not even heard of it. In 2006-07 Orkut, it's gone. It was taken by Google, then it was phased out. Then it was Facebook era. And then I think for you guys it's Instagram, Twitter, that's mostly. So those are also networks. So different networks have different kind of flows. So these are the entities, the graphs. So here these things are called nodes. The entities that you want to connect. And the connection is called edge. Okay, or sometimes also called link. The word link is obvious in the sense they are linking two things. It's also mathematical edge. Okay. Power grid networks also, what are the nodes here? It will be mostly, for example, if you have a power grid, it will be mostly the stations which generate power. So, the power generating stations. Okay. And what would be the links? The links would be the high tension lines that you see overhead, the big high tension lines. If you cross the city, you will see. So, these would be the links. Okay. So, mathematically both are same. Mathematically what they represent them as, they are like a graph, something called a graph. It has nodes, and between nodes there are these connections which are called link or edge. Oh, it's smaller? Okay, sorry. Yeah. So, it's, let me write it bigger. So, generally they are represented by graph, something called graph, where these circles are called nodes and the connection between the circles are called edge or link. Okay. Interestingly, both these networks, National Highway Grid, National Highway Network, it's sometimes called National Highway Grid also, or the electric grid, this is a power grid of Tamil Nadu or any state, or actually the national power grid. So, there is a plan for having a national power grid. So, if Tamil Nadu makes a lot of power and another state needs it, they can supply it, or the vice versa. Okay. So, now here, let's focus on road, because all of us understand road very well. We have all traveled on roads. So, what's happening between two entities in this road network? Two entities means these are, think of, they are like city. The two cities. What's happening between the two? Cars are flowing, right? So, there is a traffic here. There is a traffic. Cars are going both ways. Now, can you say that tomorrow 7 o'clock how many cars will go through that road? No. Can you predict? With what accuracy? Past data study. But can you ever be accurate? Like, in the sense it cannot be, right? So, when you cannot predict, you do not know exactly, the term for this is stochastic. Everybody heard the term stochastic before? Did you hear the term random? Random? They mean the same. They mean the same. Stochastic and random mean the same thing. It simply means there is some kind of a randomness, okay, because you cannot predict it exactly. Same thing with your power grid. How much power will be exactly needed tomorrow morning? You can predict to some extent, but not exactly. Like, you can say, maybe I have a weather forecast tomorrow afternoon, 12 o'clock, it will be 40 degrees, so the AC will be running at it full. So, mostly this much. But you may not be sure. But for example, suppose in this building, how much power will be needed? 40 degrees, if all the ACs are running in all rooms, you have a plan, like this much power will be needed. But maybe tomorrow, if suppose you don't have a class here, lecture here, this room won't be needed. So, you won't need this power here. So, everything cannot be predicted. So, here also things are stochastic. Oh. So, stochasticity or randomness is kind of part of our life. We don't know how much it is a part of our life, but it's too much. If you see everywhere, it is there. Now let's go back to our other guy, which is social networks. Okay. So that is also stochastic, but there is something more to it. Let's understand that little. Suppose I have a social network. What do you use? Instagram, Facebook? Insta. Okay. So Insta, you follow somebody, you unfollow somebody, you have some friends. So what happens? Suppose you are this guy, right in the middle. There are some people whom you follow. And maybe they also follow each other to some extent. Not everybody follows everyone. So there is this thing, connection. What it means? Suppose this is you, right here. These are your friends. Whoever, so suppose this is, I don't know, let's call it A, let's call it B. So this is generally the terms of Alice, Bob, Charles, Dennis, Evan, okay. All these guys, they follow each other. What happens on this network? What flows? Here, cars are flowing, which is traffic. Here, power is flowing. What is flowing between you? Very good. What flows here is information. Is it flowing deterministically? In the sense, every day 7 o'clock we'll put a picture or a video? Stochastic. So this is what you call a stochastic and information networks, where information is flowing and how it flows, when it flows, it's stochastic. One interesting thing which is little technical, we won't go there, information itself is stochastic. The definition of information, like the formal way of treating how much information is flowing, that itself comes from quantification of something called uncertainty or randomness. So information, the measure of information, like for example, for mass you have a measure, for time you have a measure. For information also there is a measure. Hard of bits, right? How many bits we are getting. That definition itself is stochastic, but that's a different thing, we won't go there. Now what can be the other networks, other useful networks, which are so hidden we don't see them? Pipelines, water pipelines. Huh? Very good. Postal networks, railway networks. Huh? Neural networks, okay, very good. Anything else? Huh? Airlines. You are looking too far, means good. Look. Yes, your body. Circular networks, neurons. But where? Huh? Circulatory system. Nervous systems. Your brain. Your brain is the most fascinating network. There are more connections in your brain than I think there are estimated number of stars in the universe, known universe. So it's like that fascinating a network is. So that's also network, and that's actually also stochastic. It's very surprising, the brain phenomena is also, there are a lot of randomness there. Any other networks? From, yeah, body you have covered. Now think of devices you use. Is there a network? So you have a phone, right? Everyone. Circuits, very good. Circuits is also a network. Wi-Fi networks, cellular networks, 4G, 5G. Okay. So other examples are your, let's say body, which will say many networks, brain, central nervous systems, then your circulatory networks, then your cellular networks, 4G, 5G, we'll go to 6G very soon. Then you have definitely Wi-Fi also. Then what else? We talked about the thing was circuits. Now let's stick, everybody has done some logic, like gates and gate all. It's part of your syllabus, everybody is supposed to know. Then only I'll talk about it, otherwise I'll skip. Right? Everybody knows? If you don't know, please raise your hand, we'll talk about something else. We don't have to talk about it. Not, right? It's not part of your syllabus, right? Okay. So then let's not talk about it. Okay. Let's not talk about it. We'll talk about something else. Okay. So only thing I'll just mention is the circuits, there are two kind of circuits. One is in your mobile chips. Chips which are in your mobile, in your laptop, everywhere. Everywhere there are chips. They are networks. So these guys are also networks. But interestingly, they are not stochastic. They are very much deterministic. I put it this way, deterministic for current technology. So you don't have to know about what circuits are, but your chips, the chip that runs your phones, all of you know there are chips inside your phones, in your laptop, everywhere there are chips. They are very deterministic. There is nothing stochastic about them, okay, in the sense of it can be well controlled with the current technology. So current technology is called VLSI technology. They are very deterministic. But there is a very funny story about it. Like, have you heard of, I don't know, is it part of +2 physics anymore? When I grew up, it was a vacuum diode, vacuum triode. Is it part of it anymore? No. Okay, just not need to be. So when I went to school, it was still being taught. So what happens in your chips, there is something called transistors. Everybody heard of when radios used to be called transistor long time back. Like you may not know it. I heard it. My parents definitely know about it. When first time the small radios came, it used to be called transistors. Before that, when people have a radio, it will take like the full, this window size radio, it will be there. It will be like, if you, I have seen with my grandfather's radio. I think madams, they must have seen with their grandfathers also. You guys have not seen. Your grandfather will be having a transistor most likely. So then the transistor came, which is a small radio. The whole big thing became this small. Okay, like this big. You could carry it. So what happened between the two? What happened when these big radios were there? There are these equipments called vacuum diode, vacuum triode. Okay, which were really big, and that was a different technology. That technology was in some way not exactly similar to, maybe you guys also have not seen fluorescent lamps. You have seen fluorescent lamps. Some way similar, not exactly. There are some similar, something called cathode discharge will be there, that technology. And after that came something called semiconductor technology, which is very small compared to that big size equipments. So then your transistor became, then your radio became in hand, and the technology that it used, the devices or the elements or the entities that made this possible is called transistor. And that's why this whole radio was called transistor. So what happened from there to here, it's not only the size from big became small, there was only one thing that happened was it became very reliable, because the determinism comes from reliability. They are super reliable. The previous radios, the big radios, they are not so reliable. They will malfunction. Sometimes you have to slap it. Okay. Sometimes you have to slap it in the right place, it will work, okay. Well, you won't know it, you have not seen it. I have seen it with my grandfather's, grandparents' place. So it was not reliable. And current technology is super reliable. Like how many times you have to slap your phone? Like unless you have already dropped it and broken, then it's a different thing. Your new phone, first 5 years, you'll never have to do anything. So they're very deterministic now. Now I'll tell you there's something we are going to do in future that will again become random or unreliable, but we want to do it. Does not it sound crazy? It sounds crazy, right? We had unreliable phase, we got to the very reliable era. In future, you want to go somewhere where again things will be unreliable. First, I want to appreciate the fact it sounds crazy. It sounds like humanity has gone crazy. Means humanity is crazy in many aspects. I am not denying it, but in this journey, the thing I am talking about will again go to unreliable devices. So the future, everybody has heard of AI, right? Has anybody heard of quantum technology? Yes, somewhere in the news, heard of it. So future will be quantum technology. Quantum circuits means it's not yet a real future. It will come. We are still researching, like it's an active area of research. I also work on this area. So this is not guaranteed it will happen. Nobody knows it will happen. But there is a promise it may happen. It's like a futuristic technology. Okay. Like for example, 20 years back, nobody thought that there will be a machine which can write essays for you, which can do your school homeworks. But people had that idea that it's possible. It's mathematically possible, we could not implement it. Same thing with this guy. Theoretically, many things are possible, but getting it on the hand and working it out is a challenge. So these guys will be stochastic. And they are not reliable. Now the question is, why would you like to do it if it's not reliable? Because its power is immense. It's much more powerful. What do I mean by much more powerful? Everybody has done factoring in your life, right? For example, I give you a number, 4-digit number, and tell you find the factors, prime factors. Everybody knows prime, right? Find the prime factors. What will you do? Try to think what divides it, kind of a more go by a guessing game, right? Like it's kind of your intuition. If you played with a lot of numbers, you know. Same thing in an algebraic expression. You generally play with it and figure out how to factor it. Okay. Now think of, I give you a 1,000,000-digit number. Can you even play with that? It's kind of almost impossible, like to do by. Can I write a program to do that? Hopefully, yes. But still for a 1,000,000-digit, the program will take forever to give you prime factors. Suppose if it's a 1,000,000-digit number, a program will take age of the universe to give you all the factors. And this is not bad. This is not bad because means you don't use it, but your parents use credit cards, your parents use online banking. They all are safe because you cannot factor a 1,000,000-digit number. Okay. There's something called RSA protocol, okay, which keeps your transaction with the bank secure. There's some protocol is there which all banks use. And they primarily bank on the factor that a big number cannot be factored. I can't get into the details how, But that's the main thing that makes your banking safe. Now, what quantum circuits can do, what takes the classical or even the best supercomputer anywhere in the world to as long as the age of the universe, a quantum computer, if we can manufacture it, it will factor it in few seconds. So it's that much more powerful. Okay. And that's why you want to go there. That's why I want to go there. So the hope is this. This is like a cat and mouse game. Every country is fighting to get it. Why? Once I get it, I can understand what's my enemy is talking to each other over internet. Okay. Whichever enemy you want to pick. But they are also trying to get it so that they can understand what we can go. So that is the competition. So you have a hard of, so US is fighting, India is fighting, China is fighting, everybody is trying to get it. But what will happen, these are very powerful systems. But the entities that make them, they are very unreliable. So the idea is, get a reliable computer out of unreliable components. So here, the problem becomes, get reliability using unreliable parts. So this is a very fascinating idea itself. Every small part that you're playing with is unreliable. You can't trust anything. But you have to plan things in such a way that your final thing is correct. So this is something we can't teach in +2. We don't even teach to our undergrads unless somebody is really interested in that area. I think you already had this talk by Professor Arvind Rameshwar, who talked about guessing your hat. You heard of codes there, like Hamming code. A part of this that enables these is that coding. Okay. So it has connection to that. So it's not exactly that. There are some more things have to be done, but that's again connected. Okay. So did you see this example of where, suppose I want to send a bit of information to one of you, okay. So suppose I want to send either a 0 or 1. Any question you have? Question, okay. I want to say, yeah. This unreliability means what you want to, you don't get what you want. It's not security issue. You can't control it exactly. You will go close by, but not exactly. Like think of it's like you're trying to open a lock with a shaky hand. You have a key, but you cannot point the key to the keyhole exactly. So it will move around. You have to have enough support around your hand so that you can open it. Something like that. So let me give you one example. Think of the following simple case. You want to send a 0 or a 1. So it's a thumbs up or thumbs down to your friend. Okay. And you are sending it over some scenario where suppose you want to put it this way, don't have control on your hand, like somebody is pushing your hand, or you are in a moving bus where your hands are not stable. So when you show this, it can go this also. It may not stay this. Suppose thumbs up is this, thumbs down is this. So this is my thumbs up 1 and this is thumbs down. But because of the shaky nature of the bus, your hand is either going this way or that way. So suppose I see your hand in this position, or your hand is shaking so much that it becomes like this. How do I know what you are sending? Maybe you are trying to send 1, it flipped. So how do you try it? How do you send it? One simple is yes, encoding is one, that's a, one simple is you just repeat. Suppose I tried first time, my hand shake, the bus was moving, so it went down. Next time I am trying when, maybe the bus is not shaking that time. So that time it will go through. So if I try suppose 4 times or 5 times, and out of 5 times, I decide, so I try many times, try say 5 or 7 or 3 whatever times, and take something called majority. What does it mean? Now out of that time, whatever the maximum thing I have seen, so sometimes I'll see this, sometimes I'll see the same thing I'll see thumbs down, the thumbs up I'll see as thumbs down. I tried few times and hopefully I trust that most of the time I'll get the correct thing. Okay, that's one approach. The same thing you can use it here. Suppose, who knows logic gate, suppose I want to calculate and instead of and, few times I got something else. I try few times and take majority, hopefully I'll get it correct. Okay. Exactly. You can, so you have to do it lot of times but not too many times. So you can actually exactly calculate how many times you have to do to get an accuracy of certain level. So that can be calculated. Okay. So generally it turns out that, for example, suppose if everything was reliable, your circuit was of size, an area which is 2 millimeter by 2 millimeter, a chip, then if you want to get it really correctly, it will scale up to maybe 2.5 millimeter to 2.5 millimeter. So it will go bigger but not too big. So the growing part is because of the fact that you have to try it too many times and hence you have to have extra circuits. So yeah. So when you will see a shaky hand, in your mind you will decide maybe it's 1. Then next time something else you decide 1, and whatever you decide in those 5 times, later you have to take majority of that and decide which one is going on. Yeah, it's a, oh very good, you know quantum? Okay, yeah. No, I was not trying to talk about it, but yes, you are correct. Yes, that's a very good point. So what is saying that suppose if it's universally flipping it, like it always trying to, whatever is thumbs up, it's always trying to project thumbs down. If you know that, that's actually a very good setting. Because you know, suppose you know that my friend of mine always lies. Then you can always know what is the truth. There is no issue with that. The crazy part is the guy when they lie selectively. If somebody always lies, very easy to guess. Means if it's especially a binary case, you know if it's saying 1, it must be 0. That's a good point. So that's where it comes the definition of information. It's not about correct, it's about predictability. If somebody is lying all the time, that guy is very, very predictable. So that guy does not actually distort information in a proper technical sense, because you know it will be always flipped. So it's exactly correct. You can know, you just have to flip it and get it correct. Yes. encoding is always more efficient. You have to try less. Yes. So in circuits, you cannot always do the encoding. So in circuits, sometimes you can do encoding, sometimes you cannot. So there the majority works. Yes. So there is this, everybody heard of von Neumann? Perhaps not. He is not taught in +2. Yeah. John von Neumann, you have heard of him? Okay. Yeah. So he actually came up with this whole idea of majority. So he designed this von Neumann architecture for computers, and those days when he designed it, he designed it with these vacuum diodes and triodes, these big radios. Remember? And he had to come up with to make them reliable. He did not want to go and slap the computer every time. That's not possible. It's a big computer made of 2 houses. You don't know where to even slap. So he wanted to do something reliable out of those unreliable things. He made this happen. So this is, since you know of von Neumann, I just say his name here. And this he did for classical unreliable circuits. Okay. Yeah, when you don't have majority, then you say I don't know, or you declare anything. So majority of it also could be wrong. Yes, it could be wrong. So the idea is here you will never get 100% reliability. So this is not 100%. It would be like 99.9%. So there will be always a chance you will get it wrong. So we live with that because you can prove that its full reliability is impossible with unreliable components. So during repetition, do we have a guarantee that a majority of the times the right option would be? Yes, yes, yes. So the right option will come with 99.9% that you can guarantee, but you can never guarantee 100%. So the thumbs up will all, if I want to say thumbs up, in the majority of, if I do the repetition like 5 times, majority of the times I would get the right thumbs up. Exactly. So what I'm saying, so there are a lot of tricks here also, I am hiding a lot of it. It's not majority over the whole circuit, there are majority everywhere. So a kind of majority of majorities, you do some kind of a nested majority. You take each part of the circuit, do majority, then do different parts of the circuit, do majority and combine them. It's a little bit complicated architecture. But the issue is they're again unreliable and have to put them together. And these are real practical issues where you show, and these are all very nice mathematical approaches. So I would say all of it that we discuss, the main takeaway is the following, which I want to distill out. I have not talked about any technical details yet. That we'll discuss in the second part. This is just the motivation part. Okay. So the whole thing that you see here, it's unreliable components, unreliable or stochastic components. And there is information flow in the network. This has unreliable and stochastic components and there is information flow. So the goal here is to have reliable. Again, reliable means 99.9%. You cannot have 100%. Have reliable information flow despite unreliable components. Okay. So this is I would say the holy grail of futuristic circuits and wireless communication. So how does it show up in wireless communication? That I won't get into because that requires you to understand wireless communication. I won't get there. But the same issue shows up in wireless communication. Because what you think when you're calling somebody, that you, suppose I call one of you here, you see, we are just listening to your voice very, very clearly, or I'm watching a video, it's very clear. But the wireless system is not that clear. There are a lot of issues when the information is going from here to the Wi-Fi station or even to the base station. It's a lot of noise, lot of errors, much more unreliability than even in circuits. But despite that, you don't see that. You see the video very, very clearly. And that's because people have achieved it already. So this is, again, you can't get into the details of it, but the interesting part, the way to do it, there is very interesting math here. And the math is mostly building on probability. Then you have to build on it. So I'm just trying to advocate for math and probability. Is that it's kind of everywhere now. You do communication, it's math probability. You want to do quantum, it's math probability. You want to do AI, it's also math and probability. Lot of it. On top of that, there are other math also, which you generally don't get taught. It's, you'll have something called optimization. Which is, you can think of, it's actually built on calculus. It builds on calculus mostly. So if you know calculus well, it would be useful. Then there is something called graph, which is generally called combinatorics. So all of these build on very nice math. This how to make sure you have reliable systems, or reliable, you can reach your end goal reliably with unreliable components.
How is that done, sir? Is that also the majority or encryption or
That's a little complicated. I won't get into the details of it.
But it's neither of these.
It's neither of these. This is a combination of many things. Yeah, it's there. Okay. This is just to get you motivated. I can get to the details of it. It will be too much. We don't even teach it till our second year in undergrad. Only third year enthusiastic students take it in third year. Most do it in fourth year. Okay. So I won't get into the details of it. Just trying to motivate you to how to do more math. Okay. So all these modern problems, quantum, AI, communication, you need this math. But if you love physics, there is a lot of physics in the quantum part also. So the way physics interacts is, there is physics also. So the way it interacts is, you have to come up with approaches. You come up with approach to build these systems. So you'll always, you have to, if you want to build something, it's physical, it's something there. There will be always physics. But math, what math will do, math will help to refine it. Without the math, you cannot reach its full potential. And without the physics, math cannot be put anywhere. It just stays as math. It has to be on a system. So both are needed. So better you understand both, and it would be very, very useful. Okay. So is it Keshav? Do we break here or later? Okay. So we'll break here. Next round what we'll do, I have only given you motivations. Next round we'll do a concrete thing. We'll play a short game, a probability game with coin tosses. Okay. Which will be in the setting of social networks. Thing like, suppose I'll give you the trailer. The trailer is, suppose you want to figure out there is a decision making going on. Okay. So suppose in a class, okay, you have friends, you are in a class, you want to decide, suppose today's sports period, what game to play. Will you play football, or will you play cricket, or will you play something else? And everybody has to play the same thing. Now there are certain friends who influence each other, and a decision came. And you want to figure out who influenced whom. Okay. Also note that, suppose now you go to the music class. Okay. I don't know if you have a music period or not. And today you want to play a particular kind of music. And you have to again vote on it. Maybe we'll play Western today, Carnatic classic versus North Indian, Hindustani or something. Again, people influenced each other and reached to a decision. Again, you want to figure out who influenced whom. Now note the very interesting thing here. The pattern of influencing is very different in a sports period versus a music. So the person you listen to in sports period is very different, maybe very different from the person you listen to in music. Because you think somebody is good at sports, so listen to that guy regarding sports. When it comes to music, it's different. And that happens in social network all the time. You take your advice about buying, about your parents take the advice about buying a land or buying an apartment somewhere from a certain group of people. But when your parents are asking about which school you should study and which college you should go after that, they are talking a very different set of people. It's not the same set of people you always ask. Okay. So every time the influence is changing, can I figure it out? And I can't solve the whole problem. Again, that's an advanced problem. We'll play a small game to solve a very caricature version of the problem. So that would be a little bit more concrete. Concrete in the sense we'll do some simple probability. This was all motivational. Okay, so we'll take a break for 20 minutes or